So my name is Bill Hallahan. Various portions of this are joint work with Anton Shua, Max Roy Bland, Ranjit Jala, and Ruzika Piskoch. And as Ruzika said, mixing verification and synthesis here. So I'm going to spend maybe the first half of this talking mostly about verification, but I promise we can get to synthesis eventually. Up here I have map written in a functional language. So it's taking a function as an argument. That function is mapping things of type A to things of type B. It's taking a list of A and it's returning a list of B. And so we're going to map over the list and map each of the A's to a B. And if I want to verify this, I'm going to need some specification. So I'm going to name my list that's an input X's. I'm going to name my list that's an output Y's. And I'm going to say that the size of X's is equal to the size of Y's. So map isn't changing the length of the list. And if I give this to a verifier, it will be able to tell me this is true. So in particular, the verifier I'm going to be using in this talk as an example is Liquid Haskell. I'll talk briefly about some other verifiers later on. But this is a Liquid Haskell specification. So this is a picture of what the verifier is doing, a very simplified picture of what the verifier is doing, right? We're taking code, we're taking specifications, and then the verifier is either telling us, yes, the code and the specifications match, or no, you have some kind of error. And so let's look a little bit more at this error case. So here's almost the same map function again, with the same specification. And here we're going to get an error message telling us, oh no, you have a mistake. And maybe looking at this, some of you might have already spotted the mistake before I put up the error. Now probably more of you are seeing it, right? I've not consed anything onto my list, so I'm just always going to get an empty list here. But even with just this pretty simple piece of code, I'm getting this big error message with all this information in it, variable names that I haven't used before. And it can be kind of difficult to figure out what's happening with these errors as your code gets bigger and bigger. And so what we might like to have instead is just a counterexample saying, no, if you apply map to the identity function and a list with 1 in it, you get an empty list and you've violated your specification. And so I worked on, with my collaborators, a symbolic execution engine named G2 that can find these kind of counterexamples for these kinds of specifications. Now, what's unfortunate is in some cases we can't find counterexamples when you get a specification error, or at least we can't find this kind of counterexample, because Liquid Haskell is something called a modular verifier. So other modular verifiers include ESC Java and Daphne, for example. They would all have exactly the same problem I'm about to show you on the slide with slightly different syntax for code and specifications, right? So modular verifiers means sometimes we can't find nice, neat counterexamples. And here's why. I have a much simpler function than map. Actually, up here I have a function called add2. Add2 is taking an int as an input, and it's returning an int. And the specification is saying that the output should be exactly 2 more than the input. And the definition is calling infer twice. So let's look at infer. Infer, the specification is saying I'm going to return a number that's greater than whatever I put in. And I'm accomplishing that by just adding 1 to my input. So you might look at this and say, OK, this looks good, right? I am going to be returning a number that's greater than my input. I'm adding 1 twice, so that's the same as adding 2. This should all check out and be verifiable. And in fact, that's not the case. We're going to get an error message if we give this to Liquid Haskell, or again, any modular verifier. And the reason is that when verifying a caller, a modular verifier is not actually looking at the entire picture that I have up on the screen right now. When verifying add2, a modular verifier is going to look at this part of the picture. It's going to look at the specifications of functions that are being called, but it's not going to look at the definitions of functions being called. So when verifying add2, we know infer returns a number that's greater than its input, but we don't know by how much. It could be that we're adding 1 million on, and then infer specification is satisfied, but add2 specification is not. And so the way we need, Well, OK, and so then the question is, how do we fix this, right? And again, this error message doesn't give us much of a clue. And so what we can find using G2 with symbolic execution is what we call an abstract counterexample. So this is an abstract counterexample for this case. So the abstract counter is saying that add2 of 0 is equal to 3, violating add2 specification if anchor of 0 is equal to 2. So there's a counterfactual here, right? So anchor of 0 doesn't equal 2. But the point is that anchor of 0 could equal 2, according to the specification of anchor. And if it did, then add2 of 0 would equal to 3, which violates add2 specification. And so the way to fix this is to take anchor and strengthen its specification to rule out this bad mapping. So if you do that by saying that anchor has to exactly add 1, then you'll be able to verify this program. Here's a little bit of a bigger, more realistic example. I have a concat function up here. The idea is concat is going to take a list of lists, and it's going to join all of those internal lists together into a single list. So I take a list of A's, and I turn it into a list of A's. And the specification is saying that the size of the output list should be equal to the sum size of the input list. So I'm not showing sum size here, but sum size is just taking each of the internal lists, computing its size, and then summing those up. So I have concat. Concat is self-recursive and also calls this app function. App is just appending the first list to the second list. So I take a list X, I take a list Y, and then I get the list XY. And I'm saying that app should return a list that is longer than both of its inputs. So the size of Z should be, the size of the output should be greater than or equal to the size of the first input and greater than or equal to the size of the second input. And we're not going to be able to verify this if we give it to our modular verifier. And we can get an abstract counterexample that illustrates why. It says that concat of a list with 1 in it and an empty list can give us the list 1, 2. If appending list with 1 in it to an empty list gives us 1, 2, right? So notice this has size 2, this has size 1, this has size 0, 2 is greater than 1, 2 is greater than 0. So this satisfies the specification of app, but causes a violation in the specification of concat. So again, the solution here is take app, give it a stronger specification that rules out this possibility. So in this case, we have to say that the size of the output is exactly the sum of the size of the first list and the size of the second list. And then we'll be able to verify this. So here's my slightly modified picture now. I still have this verifier up here. It's still taking the code and the specifications. Ideally, everything just gets verified, and we're happy, and we have code that works. But if verification fails, we can go and we can find either what I'm calling a concrete counterexample, just kind of a traditional counterexample. Here's an input and an output that violates specification. Or I can find an abstract counterexample that is illustrating why a specification is too weak to allow verification to succeed. So we want our symbolic execution to be able to find both of these kinds of counterexamples. So to do that, we do a bit of an instrumentation on the code, and then we run symbolic execution. So I'm going to show you what that instrumentation is, and then a little bit of a trick we do while symbolically executing. Here's my add2 anchor example from before. And here's the instrumented version of the code. So add2, nothing that interesting has happened. I've taken the definition of add2, stuck it in a variable, and then I have an assertion that just corresponds to the specification, and then I'm returning whatever add2 returns. Anchor is a little bit more interesting. So anchor has a non-deterministic choice in it. And on the left-hand side of the non-deterministic choice, I have, again, the definition of anchor, an assertion that corresponds to the specification of anchor, and then I return whatever anchor returns. But on the right-hand side, I have this syntax here. So this question mark is going to return a new symbolic variable when we run it in our symbolic execution engine. So we get a new symbolic variable. We assume that it satisfies the specification, and then we return that new symbolic variable. And so you can think of the left-hand side of the non-deterministic choice as corresponding to concrete execution. And if we go down symbolically executing and we find a branch where we've only taken the left-hand side of the non-deterministic choices, we've only done concrete executions, that corresponds to a concrete counterexample. Whereas this right-hand side, we're abstracting away the definition of the function, much like the verifier is doing. So we can take any value that satisfies our specification and return it. And so branches where we take at least one right-hand branch of one of these non-deterministic choices correspond to abstract counterexamples. So here's how that plays out in the add to infer case. We have our code. We have our initial code, the code for add to. Because it's symbolic execution, we're going to branch into different possibilities when we hit something like a non-deterministic choice. So we're going to execute infer and say, OK, over here, we've taken this infer, expanded it out to x plus 1, the definition of infer. Over here, we have this assumption from the right-hand side of the non-deterministic choice saying, infer has some behavior, but we don't know what it is besides it satisfying this assumption. And then again, we have another call to infer in both of these. So we branch into two more possibilities, right? So we have a case over here where we've executed infer twice concretely. We've just added one twice. And that is going to not violate the assertion, right? So we haven't found an assertion violation there. And then in all of these other cases, we've abstracted away the definition of infer at least once. And so these will all be able to violate the assertion because infer could have returned any number greater than its input. And in practice, we discard this one. This is the state where we've abstracted infer twice. Because we have two other states where we've only abstracted infer once. And so these more precisely indicate the function call that has an incorrect specification. So this is actually more important if you have many functions, not just one, right? So if we had another infer by 5 function that had a precise specification, these would precisely identify infer, not infer 5 as the problem. So that is what concrete and abstract counterexamples are. That's how we find them with symbolic execution. And the initial idea here, so this was published in a paper at PLDI 19 with all of the collaborators on the first slide. And the idea here was, you could use this to help debug when you're using a modular verifier. You could get these counterexamples and then manually go and fix your specifications. But of course, there's something better we can do. So we can use synthesis and turn this into a CGIS loop and automatically find the specifications that we need to let the modular verifier prove our code correct. So I've made this picture a little bit more complicated. So still take the code and specifications, go to the verifier, hopefully everything works out. If it doesn't, go to G2. And then there's a couple different possibilities of what can happen. So the first is, our assumption is the user is still going to write down some specifications that they want to prove are true, and we should aim to prove those are true or tell the user that those specifications are wrong. So we might find a concrete counterexample to the specifications the user wrote down, and in that case, we're still just going to report that to the user, right? Because then we don't know how to fix that automatically. So we might report a concrete counterexample to the user. But if we find an abstract counterexample, we can give it to a synthesizer, synthesize some new specifications, and go back to the verifier, and then just do a typical CGIS loop where we repeat this process until the verifier is happy. And of course, at some point in this process, we might find a concrete counterexample to a specification that we synthesized. And then again, we can just give that to our synthesizer and ask it, OK, take this concrete counterexample into account, come up with a new synthesizer that doesn't fall prey to this. Right? So here's how that works in practice. This is my concat app from example from before, except I've completely removed the specification from app. And so, of course, what's going to happen is modular verification is going to fail because it doesn't know anything about what app here is doing. So we're going to get an abstract counterexample that tells us that if we concat a list with an empty list and an empty list in it, that can give us a list with 0 in it. If appending an empty list and an empty list gives us a list with 0 in it. And in fact, we can also just run app concretely on an empty list and say, what does app actually do, right? Well, appending an empty list to an empty list gives us an empty list. And so now we have two goals for a synthesizer. We need a specification for app that is false on kind of this spurious case that causes verification to fail, and that is true for what app actually does, right? And so we're going to give that to a synthesizer, and it's going to tell us, okay, well, maybe the size of the output is always 0, right? It's a problem if the size of the output is 1. You're happy if the size of the output is 0. Maybe that's a good specification. Well, no, of course. Now we can come up with a concrete counterexample that says appending a list with 0 in it to an empty list gives us a list with 0 in it. So we have another goal for a synthesizer that corresponds to this counterexample. So come up with another specification, right? Size of the output should be equal to the size of the first input. Well, no, we get another concrete counterexample where the second list has something in it. And so we just repeat this process over and over until we reach a correct specification for app. We have an algorithm and an implementation that does this. We have theorems associated with that algorithm that I have kind of heavily paraphrased on this slide. Soundness follows quite easily. So you have a sound algorithm if you have a sound verifier, because the verifier is going to reject anything that's not correct, right? So as long as your verifier is sound, we're not going to be able to verify specifications that are incorrect. We have a more interesting result, I think, in that if there exists an assignment of linear integer arithmetic specifications, so specifications drawn from this grammar, to functions such that verification would succeed, we will eventually be able to find that set of assignments. So again, there's quite a bit of nuance lost in how I kind of squeezed this onto the slide. In order to have this, you have to make some assumptions about what your synthesizer is doing, but those assumptions are not overly onerous, and I'll get to those pretty shortly. I'm actually going to get to them now. So the way we're going to design our synthesizer is we're going to encode synthesis of Lia formulas as an SMT problem. And so we have this little synthesizer down here that is giving us the specifications for our functions. And we're going to use an SMT solver to solve this problem. And what we're going to do is have templates. So this is a portion, I guess I say it's a template up here, but it's a portion of a template where we're basically saying we might want an equality, we might want to have something that's based on a less than or equals, or we might want to use a less than, something that's a less than or something that's a less than or equals. And our specifications are over a bunch of values, which correspond to x1 to xn here. So those are values that would be concrete and are coming from our counterexamples. And then C is the coefficients for those that would be appearing in the specification. And because we're trying to synthesize them here in the SMT problem, they're variables, unknown variables that we need to solve for. So each of these xi is either an integer value that comes from the program, or it's somehow computed from something in the program. So it would correspond to size of a list, for example. And in order to account for the possibility of conjoining or disjoining multiple Lia formulas, we slowly grow the size of the specifications in our SMT template over time. So initially, we begin with a template that does just look like this. But then if we can't find specifications that have this form, if the SMT problem returns unsat, we say, OK, what if we have this conjoined with another template that has the same shape? Or what if we have this disjoined with another template that has the same shape? And so by doing that, we can find conjunctions and disjunctions of Leo formulas. So we've evaluated this on a number of benchmarks that are drawn from mostly existing sources. So they're drawn from a combination of homework assignments that were used in classes teaching about liquid Haskell, and a book that was written about liquid Haskell, and some other kind of blog posts online. And for the most part, we can automatically verify the correctness of the specifications in these in under a minute, in some cases in seconds. There's a couple of timeouts. So in theory, we should be able to find specifications for those. And if you ran the tool for long enough, it would. But actually, what's happening in most of these timeouts is our symbolic execution engine is falling apart a little bit and failing to find counterexamples. And we're having to fall back on other ways to drive the synthesis forward. So in particular, just negating the model we got from the SMT solver before. But in most cases, it works well. We also have one benchmark that is significantly larger than all of these. So that is the inner loop of a k-means function. So this is the code for the function that is the inner loop, so kind of the main function in the file. And this is calling 5 other functions that all need to be given correct specifications that kind of interlock with each other. And in total, there's 34 functions in this file that need to be assigned the correct specifications. And our algorithm succeeds in doing that in 457 seconds. With that, that's I'll conclude. So talked about finding concrete and abstract counterexamples to debug modular verifiers, and then how we can use those to automatically find specifications to allow for modular verification. Thank you, and I'm happy to take any questions.
Thank you, Bill. Let's thank the speaker. Questions?
There are a couple of buzzwords that I'm surprised you didn't mention. Strongest postcondition, weakest precondition. What happened to these guys?
Yeah.
They seem to be very incredibly relevant to modular verification. The problem was that the human written specification was too weak, right?
Yeah.
It wasn't the strongest postcondition.
Right. So, yeah. So, I mean, certainly, like, the add to infer example is a little bit silly, right? But really, because we're in because we're in a functional setting here, we're using recursion, right? And so we're essentially trying to find loop invariance. So I think you're probably correct. There's ways we could take weakest preconditions, strongest postconditions, and use those to further inform, the process here and help us maybe more quickly actually narrow in on what does that essentially loop invariant need to be. But it's not going to solve the problem in and of itself. For the same reason you need to provide loop invariance.
You need what? The same reason?
The same reason you need to provide loop invariance.
No, I mean, we don't always have an automatic way of getting these objects, okay?
Yes.
But essentially, these are the elements that you need, I think, for modular verification that are exactly that. Strongest postcondition and weakest precondition.
Right. Yeah.
So just please take into consideration.
Sure. Yeah. That is what the verifier is using under the hood, right? But we're essentially trying to find loop invariance.
I have the same question, but the opposite. So actually, when you have several functions, no. I would think that actually you don't want to do weakest precondition or strongest postcondition because they may be just too difficult to express. So you want to find some invariant that shows that your whole program is correct. And what is your strategy? You will just go to one place and go for the best invariant in this place, and then go to another place, and or
No,
you
so
go
I-
breadth first. And but what it means breadth first in this sense? Because
Yeah, I didn't really talk about this, but really what we're doing is starting from kind of the root of the program, which typically is going to be functions that the user has exported and actually cares about and written specifications for, and then kind of working our way down, right? So, this is kind of a boring example because there's two functions, but suppose append called another function, right? We'd say, okay, we want to prove this specification for concat. So what has to be true for concat? What has to be true about app to allow us to prove the specification for app? What has to be true about app in order for us to prove the specification about concat? And we come up with some specification for app that at least we can't find a counterexample for, a concrete counterexample for, and that, if true, would allow us to prove the specification for concat. And then we go on and say, okay, now we need to show that app is correct. App calls some other function. So let's go to that other function and see, can we come up with a specification that supports the specification we came up with for app? It's kind of working down from what are the specifications we know we definitely need to prove, what are specifications that would let us prove it, what are specifications that would let us prove those specifications, so on and so forth. It is a tree. It's not a straight line down. Oh, so we're taking an entire level of the tree at one time, I guess. And there's maybe cases where you could heuristically say, it's better to go one way or another. Because also, it's not even necessarily a tree. It could be a graph, right? There's maybe more work that could be done in heuristics there, but we're just going down and saying so it's a breadth first search, I guess. Yeah.
Are there more questions? So if not, let's thank speaker once again, please. And this concludes the talks for today. So now we are going up there again for our tea time and a coffee, so we can continue with discussions that we started already before. And remember, tomorrow is holiday, so Institute is closed. So you also have a holiday, which you can spend however you want, or you can agree with your colleagues to continue working, because that's how we spend our holidays, right? But jokes aside, so we will, that's kind of enough of the talks for today. We will continue back on Friday at 9:30. And also one reminder, please test yourself. We just want to make sure that everyone is healthy. And again, please follow all the the suggestions from that were sent to you by Moshe, and also that CDC is giving. Okay. Something else? Happy holiday. Happy holiday.